is happening, and I am so grateful to all of you joining us, and especially to our guests who will be speaking this evening on this second session of 3 in this series on climate change. And just a couple little tiny housekeeping things with Zoom. Many of you are using Zoom regularly, so you're veterans at this even more than I am, I'm sure. But when we have the speakers talking, I am going to mute everyone else, and I just have the speakers unmuted, and I will put it on speaker view as well. So that hopefully you'll just see that person. Okay. That's me. Okay. Hang on a sec, just trying to, it's kind of hard to both type love notes and talk to the group at the same time. So please be patient with me. All right. So let me see what I can do here with that.
You're getting pretty good at this tech stuff.
Let's see. So, Greg, I see an option on my computer to make a host. I think I'd have to go back into the software to make it a co-host, I think. We're trying to make it so that the guests can share their screens.
Oh, there is?
Okay.
Okay.
Okay, I see now. Okay. Here we go.
If you bring up the participant list.
I got now, Heidi was helpful to say that I can enable guest screen sharing. So now
you can hover over the
well, it says,
over the participants' name there, and you'll see something that says more. And then if you click on more, it will allow you to make co-host or something along those lines.
Yeah, that's what I thought, but it only offers the option of making the host, being the host, not co-host.
Oh,
but I have on the share screen, though, on the share screen, on the advanced sharing options, I've clicked on that who can share, all participants can share, who can start sharing when someone else is sharing, all participants.
Okay, well
So
that sounds pretty universal.
Yeah, okay. So hopefully that will take care of it. We'll trust it will. Sorry, I didn't have that planned beforehand. Okay, so welcome everybody. It's good to see you. Thank you for being here again. And this is the second of 3 sessions. Last week, we were sharing on the way in which the whole globe is affected by the climate change that we face. Today, we're looking at regional impacts of that. And we are very pleased to have with us today, again, Dr. Greg Garfin, who's going to present on Southwest Climate Change Overview, a climatologist from the University of Arizona, and Mike Crimmins on the climate variability and change, Laura Marshall on Arizona climate and fire, and Holly Richter on the San Pedro River flows, ecology and climate. We'll have a question and answer time and closing remarks and preview. So as mentioned before, I will seek to mute everybody but the speaker and try to have speaker view only for those that are speaking so we can have that focus. And if you have questions, if you could keep them to the end, that'd be great. You can also include those questions in the chat room and direct them at various speakers so they can help to address it in that way. If you want to raise your hand at some point, you can do the reactions down below as well. So thank you. And if I could, please lead us in a short prayer to ask blessing on this time together. Gracious and loving God, we thank you for bringing us here this evening. We thank you for all those who are gathered here on our Zoom chat and those who are also gathered on live stream, both who are watching now and will watch later. We pray, Lord, that you would bless all of our speakers, both in what they share this evening, that it would be helpful to all of us to understand better the complexity and the issues and the wonder and the intricacies of your creation, that we can better understand how we might live as better stewards and as those who enjoy this creation as well. We also ask your blessing on each of our speakers in their work, in their lives, and in all that they're about, that they would continue forward now and into the future fruitfully to the caring of this natural world and of themselves and others as well. So we ask again your blessing on this time, and that it may provide what you know that we need to hear at this time, so that we then can respond and can act in ways that would be faithful to who you have called us to be. We'll pray this in your holy name. Amen. And now I'm going to turn this over to Dr. Garfin to talk about the general overview and introduce our speakers as well.
Thank you, Pastor Mark. Let's see. There we go. All right, that's working correctly. Then you see a title slide here that introduces the title of my talk. And before I get to that, I wanted to follow up on an issue from last week. Someone asked about summer precipitation and noticed that the summer precipitation had been decreasing where they are, presumably in Sierra Vista. So I got this graph from the Western Regional Climate Center looking at the total July and August precipitation amounts for Cochise County back from 1895 to this year, so July and August of this year. And, you know, I was a little bit dismissive of the person's remark last week saying, well, yeah, it's not really decreasing. It varies a lot because I tend to focus on all these ups and downs in the precipitation that we see in these different the levels in these different bars here on the graph. But what I failed to focus on was these last several years where, yes, indeed, the precipitation has certainly been below the long-term average, which is this black line going across the graph. So thank you for your observation and for taking me to school on this one. So thanks for that. I'd like to introduce our speakers for this evening. Mike Crimmins is professor and extension specialist in the Environmental Sciences Department here at the University of Arizona. And he's the first guy that I would go to in asking questions about Arizona climate. Dr. Laura Marshall, recently Dr. Laura Marshall, she's been working as a postdoc here at the U of A, and she just got a postdoctoral research position at the Rocky Mountain Research Station at Colorado State University, where she'll be working on post-fire seedling survival from restoration planting efforts. And her 2019 dissertation addressed tree growth and species response to climate, topography, and altered fire regimes in Southwest forests. And then Holly Richter is the Arizona Water Projects Director with the Nature Conservancy in Arizona and a longtime resident of Southern Arizona. So my pleasure to introduce those folks, and we'll be hearing from them soon, shortly. So without further ado, I'm going to give an overview of climate changes, observed changes, and projected future changes across the broader Southwest. I'll point out some implications for Southern Arizona, which I hope will be a good lead-in for Dr. Crimmins. So when I say Southwest, I'm referring to this 6-state region stretching from California across to Colorado and New Mexico. This funny red-colored region here, these are the regions that we used in the National Climate Assessment. And I'll just note, I think echoing a point that Katharine Hayhoe made last week, that these climate changes are superimposed on all sorts of other challenges that we have, such as the reliability of our water supply, increasing population across our region that puts more stress on resources. Lower left there, invasive vegetation and insect and wildlife species that also stress ecosystems. And then our growing urban regions that can fragment the landscape and make it harder for wildlife to thrive, and also puts a lot more people out on the landscape doing fun things like going camping, but that can also ignite more fires and put more stress on our landscapes. Anyway, that's just a background to all the climate stuff. So I'd like to start out with some observed climate changes, focusing on our Southwest region. This graph over to the right is the average decade by decade precipitation across our 6-state Southwest region. And if we look at the graph, we can see that there have been some wet periods, some dry periods, droughts, some wet periods. If you lived here in the early 1980s through the early 1990s, it was pretty wet. And then our most recent dry period. By and large, it's a lot of variation from decade to decade, also from year to year. And I think maybe Mike will talk a little bit more on the year-to-year scale. At any rate, there hasn't been any really large upward or downward trend in the precipitation overall. And this variability is what dominates, and we know that the things that contribute to that variability are the interactions between the atmosphere and the ocean, primarily over the Pacific. Here's a similar graph. This is the annual decadal temperature across our 6-state region. And again, we see some cool periods and some warmer periods, and cooler and warmer. But something that distinguishes the temperature record is this strong upward trend in temperature, which is in line with the global increase in temperature that Katharine Hayhoe described last week as a result of increase in heat-trapping gases that's changing our global and regional temperatures. So you could imagine that if temperatures are increasing, but precipitation is dominated by that variation, the variability, that there will be some effects of that temperature. And some of the effects that we've seen are a decrease in soil moisture across the region. There have been impacts to snowpack as well. So there's been a decrease in snow water content. So for the same volume of snow that we might have taken back in the 1950s compared to that volume today, if we melted it all down, we're getting less water out of the snow. There's also a decrease in snow-covered area across Western North America, and we're seeing earlier melt-off of snow in the spring season. And these sorts of things have contributed to what hydrologists call reduced runoff efficiency. So basically, for the amount of precipitation that we get, especially snow, we're getting less bang for the buck, and that means less of that moisture is getting staying in the soil, getting into our streams and our reservoirs. Also, increases in temperature have effects on the life cycles of plants and animals, and we've seen some interesting mismatches in the timing of when, let's say, some migrating birds show up and when their food sources blossom, and that can affect their ability to breed. Increased temperatures can affect the breeding of insect pests, shown here in the lower right, and can also affect the ranges where we find the elevational ranges where we find vegetation in our mountain ranges. And Dr. Crimmins has done some work on that particular issue. We've also seen, with a longer snow-free season and hotter temperatures and more drought stress throughout Western North America, including the Southwest, we've seen massive die-off of conifer trees. We've also seen an increase in the acres burned across the region. In fact, across the Western United States, it's estimated that the number of acres burned has, due to climate change, is double what that might be without climate change. Again, due to the effects of temperature on fuel moistures, as well as having a longer and hotter snow-free season and fire season. Ironically, as the temperature increases, the atmosphere can hold more moisture. And our colleague Chris Castro at the University of Arizona has shown, and his research group has shown, that heavy summer precipitation has been increasing. So not the overall volume or the amount of precipitation, but when that precip does come, and I know that this year's a big anomaly to that, it's coming in more intense events with longer dry spells in between. So these are all things that we've observed. And then using climate models to look into the future, I'll describe a few projected changes. So one of them is projected temperature changes, and I'm showing two maps of North America with temperature changes based on assumptions of continued high emissions of those heat-trapping gases for the middle of the century, roughly 2040 to 2070, and then for the end of the century over here on the right, 2070 to 2100. And what we can see is that with these assumptions of continued high rates of emissions of heat-trapping gases, annual average temperatures will increase on the order of 4 to 6 degrees Fahrenheit by mid-century, and almost double that by the end of the century. Annual average temperatures, a tough one to wrap your or my head around anyway. But to give you an idea of that, Tucson's annual average temperature is about 69.5 degrees Fahrenheit. Sierra Vista, at a couple of thousand feet higher, the annual average temperature is about 6 degrees lower. So if we continue on this path of high emissions, Sierra Vista's future temperatures are projected to be more like those of Tucson in the future. Increased temperatures increases the breeding season for insect pests, and this could have some ramifications for public health. It's not so much that we'll be swarmed by jillions and jillions of mosquitoes, but we'll be exposed to mosquito bites over a longer period during the course of the year, and that'll increase our exposure to disease. Increased temperatures are projected to decrease soil moisture. We're pretty confident about that, particularly in the winter, spring, and summer seasons. Increased temperatures, again, through their impact on snowpack and evaporation, are projected to decrease the reliability of water, surface water, notably in the Colorado River system, where recent research shows that for about every degree Fahrenheit increase, stream flow decreases by around 5%. With increased temperatures, the number of large fires is projected to increase. And overall, again, largely due to increases in temperature, our region has been aridifying, and it's projected to continue to aridify into the future, with the qualification that as the atmosphere warms, it can hold more moisture, and we anticipate that heavy precipitation will continue to increase in the future. And just a little note to bring things a little bit back to Catherine's talk last week, thinking about agricultural imports to Arizona. We import something on the order of about 95% of the food that we eat in southern Arizona from other states or other countries. And we import about $250 million worth of agricultural products from Mexico, including vegetables, tubers, nuts, and fruits. So we need to think also about how climate change affects other parts of the world because of that chain of goods flowing in from other countries to Arizona. So I've bashed you with a whole bunch of doom and gloom here, and actually that was partly the purpose of our session tonight. But I'll leave you with a little bit of hopeful stuff that we'll follow up with maybe in questions a little bit later, and certainly in next week's session. So some things that folks are doing in Arizona and in the Southwest to adapt to climate changes include partnerships such as between federal land management agencies like the Bureau of Land Management in its management of the Las Ciénegas National Conservation Area, a little bit to the west in the Sonoyta Valley. They're working with folks, including the Sonoyta Valley Planning Partnership, to implement measures that make the landscape a little friendlier for vegetation and wildlife to be more resilient to projected future climate changes. There are also these forest fund initiatives where folks are either paying for forest treatments to reduce the chances of these really severe stand replacing fires either through their monthly utility bills with water utilities, or in the case of a community like Flagstaff, they taxed themselves to pay the Forest Service to do some treatments in their watershed to reduce the risk of catastrophic fires. Water managers have been thinking about the climate change issue, believe it or not, throughout the Colorado River Basin. They have a whole array of tools for adapting to change, including more water conservation, storing water underground through water banking, building new reservoirs, and desalinating ocean water. And I'm guessing that Holly will talk about some other measures in addition to these kinds that allow us to increase the reliability of water supply in our rivers and groundwater. And then some cities, Tucson's only one of them, are engaging in various kinds of measures to reduce emissions and improve resilience. And I expect we'll go into that in a lot more depth next week. So with that, I will stop sharing here and we can hand it off to Mike Crimmins. And please put your questions in the chat window and we'll get to those a little bit later.
Thanks, Greg. Can you hear me okay?
Yes.
Okay, I've done this probably 30 times in the last 30 days, but sharing my screen is always a challenge for me. Let's see here. Okay, 1 second. We'll try again here.
It looked like you were doing it.
How'd that look? Do I happen to have the right screen up by any chance?
Not now. You did.
Not now? Okay, just 1 second here. Let me try that
You did
again.
have it. It was up before.
What's it? Okay. All right. Presentation? Maybe? Okay, great. I will get this right someday. Thank you so much for having me. Greg, thanks for the kind introduction. Pastor Mark, thanks for having me here. My Zoom lags, my video lags a little bit, but hopefully my voice will keep up with my presentation here. So just gonna jump right into it. So I'm gonna talk about tonight is, and Greg set me up just beautifully, and I really appreciate that, Greg, is I'm gonna zoom right in and actually use some of the same figures that Greg had used, but they're gonna be a zoom in on Cochise County and specifically on close to the Sierra Vista area. And when I think about climate change, I like to think about climate change specifically about Arizona, but through this, an understanding of the template that climate change is gonna be expressed. So what are the main controls of that control Arizona climate? And so I'm not from Arizona originally. I've been here for 20 years now, but I'm from Michigan, so I'm a Midwesterner, and I'm still just amazed by the variability that Southwest climate can throw at us who live down here. And it's such a challenge to try to get our heads around how different the climate of the Southwest is from the rest of the country. We have things like topoclimate, so that's basically the extension of climate on topography. We have topographic variability across the state that leads to amazing biological diversity just on elevational gradients. And we also have seasonality. So we have topographic variability and we have seasonal variability. So there are very few other places in the continental US who have those kind of unique factors working together to create variability over space and time. So we have monsoon season and we also have winter storms. And so we can get snow in one season that is draped across the high elevation areas. And then we can have monsoon storms that will pummel those high elevation areas, but then move into valley locations. So it can create amazing spatial variability. We also have, as Greg talked about earlier too is we have longer term variability on the order of decades, 3 to 7 years with the El Nino Southern Oscillation, and then over periods of decades that can create long-term drought and longer term wet periods. So, and then we also, as we're talking about through this series here, is we have climate change on top of that. So warming temperatures, the shift from snow to rain, and the idea of increasing evapotranspiration, which actually increases aridity in the background. So we're always coming and going, and it depends on where you're at and what season you're in to really get a sense of what the climate is doing at any given moment. So having this enormous background variability makes it kind of hard for us to pay attention to climate change. So I think we have to kind of keep our eye on the idea that we live in an extremely variable place, but it's also changing at the same time. Okay. So here is a map here. I'm going to kind of show you some visual aids here to just think about this topoclimatic variability. So this is a gridded map of annual average temperatures. Sorry for the degrees Celsius. Just have to do the conversion in your head there. But it gives you a sense of where those topographic ranges are and how they lead to cooler temperatures at higher elevations and those hot temperatures as we get lower in the desert. We all know this. We've all hiked. We've driven up these mountain passes, and we know that the temperature goes down. But that's really critical in understanding longer term variability and longer term changes to the region, is that we can have changes over small spatial distances that can lead to large differences in hydrology and biodiversity. At the same time, we also have on the temperature side, we have that even change as we go up in elevation, and we have something similar in precipitation, but not quite. It does get wetter as you go uphill in Arizona, but not always and not consistently across space. So that leads to another dimension of the spatial variability of climate, is that precipitation varies dramatically from season and over space in relation to topography. So you can look to the northeast part of the state. That's actually a high, cool desert in relation to the rain shadow of the Mogollon Rim. So as storm systems come in from the west and move from west to east across the state, they're forced up that elevation range, which causes precipitation. The air then descends on the other side into that high, cool desert and dries out. So it leaves less moisture available for precipitation. We can look down in southeast Arizona, and we actually have a basin range topography with our sky islands. But you may notice there too is that those intervening valleys are a little bit wetter than some of the other same elevation places in the state. And that's the monsoon season. So having storm systems that form on the top of mountains, thunderstorms that form on the top of the mountains, can move into the valley locations and even out a lot of the spatial gradients that happen during the monsoon season. Not always, and certainly not this summer. And then let's think about over time. So this is the seasonality aspect, which is through a year, we have distinct, and I have to use my air quotes, wet seasons, because I think somebody who's from back east wouldn't necessarily consider them wet. But for us, they're really important. And so this graph here is on the y-axis, which would be up and down on the where inches are the inches, the total long-term average monthly precipitation in inches. And this is a cookie cut out of Cochise County. It's the same data that Greg just showed you with the declining summer precipitation. And this black line is called the median, which is the middle. If we organized all of the data in rank order from biggest to smallest, what's the middle value? And so that's going to give us an indication. It's similar to what we consider the average, depending on the distribution. But then it's organized around this black line of the values closest to it, and then further away from it are they're rarer values in the distribution. They're occurring less frequently. So this is through the water year. I threw you a little bit here. It's not the calendar year. It's not starting in January, but it's October. So it's October all the way through September. And again, these are long-term pattern here. So this is the whole data set from 1895 through 2020. And if we rank order that and we look at this monthly pattern, it gives you an indication. Here's our wet season. So we get into, and it's really kind of hard to see here, October is this wide band of variability, typically kind of on the dry side, but can be very wet. And that's because of the influence of tropical storms in some years. So they can be extremely wet months, but most of the time you get nothing. So that leads to a very high variability in the long-term record. Then it declines a little bit in November, and then we get into this little more reliable wet season. The further south you are in the state, you're further away from that storm activity. So you go further north to say Flagstaff, this gets a bit higher. And so they have more reliance on the wintertime precipitation. But you can still see here, there's a little bump here, December, January. We reliably decline through March and April, through the winter storm season into spring, which I always argue is a generous term for Arizona. It's arid foresummer is in the literature as well, because it can be very hot and very dry in April, May, and June, and typically is very reliably. And then we move into that really distinct shift into the wet, typically wet. I say that as though that happened this year, and it certainly didn't. Season of the monsoon. You can still see wide variability around July, and it usually tightens up a little bit in August, and then we quickly get out of that season. So you can kind of think about this, kind of rinse and repeat every year as we're moving in from one season, we're reliably dry in the spring, we're anticipating the monsoon, we're getting out of the monsoon, we're looking to October. Is it going to give us a tropical storm? Probably not. If it does, it's a huge benefit. Then we look to the winter season. So we're constantly doing this dance of looking to wet season, and then just relaxing in the spring because we just know it isn't going to rain. So that template is really important for us to think about climate change into the future. And then on the longer term variability, and I don't want you to, it's like 7 o'clock on a Wednesday night. Do not stare at this graph too long. I'll give you real quickly here. This is the relationship for Southern Arizona of El Nino, Southern Oscillation. So La Nina events are blue dots and red dots are El Nino events. And in between are this neutral period. Is that in wintertime, so we think the cool season, October through March, we take all of those, and this is for all of Southeast Arizona, if we take all of the wintertime total or cool season total precipitation, we organize it, if it was a La Nina event, a neutral event, or an El Nino event, you get this kind of real rough organization though, where in El Nino years, they can be quite wet, the stronger the El Nino event, except for 2016, which really let us down. And then, but if you notice these blue dots are pretty reliably dry for Southeast Arizona. And those are your La Nina events. And so we're actually using this as a forecast tool. And we have a La Nina event that has developed and is now expected to be mature in midwinter and probably will linger into the spring. That is the situation where we can, with as much confidence as we have in sort of seasonal forecasting, which isn't a ton, but this is that rare instance where we can say, you know what, this winter's probably going to be dry, because in the past, this is the patterns emerged, and we know dynamically what that does to the pattern. So we're looking at a very dry summer and now a very dry winter. So this is a real kind of bummer here. So it's not only longer term doom and gloom, Greg, but it's also a bit of shorter term doom and gloom too. And I calculated it's 263 days till the next monsoon season starts. So we can put that on our calendar as well. And just real quickly, the way we know that these pattern shifts happen are during La Nina events. It tends to move the jet stream, park it over the Pacific Northwest, and it leaves the southern tier states dry. A bit of the opposite happens is that we end up having a more sustained storm track over the southern states, including us during El Nino events. So that's how we know we see in these longer term patterns. And I'll try to talk about that a little bit more. Okay, so Greg, thanks for teeing me up. This is almost the same graph that Greg showed, but now we're actually going to look at 12-month precipitation for the period of record for Cochise County. So this is kind of interesting because so it's through August of 2020, and you have to go back 12 months. So it's September through August. So it's a weird time period, but it's consistent over the whole period of record. And so it shows that same element of decadal variability that Greg was showing here. You can kind of squint here, but you see this orange line, kind of wettish, dryish through the 50s, a bit dryish through the 60s, wet period through the 80s. We bottomed out here in kind of the 2002 drought. 2011 was certainly a dry year, kind of marks some of those. And there's this nice little uptick here, which is certainly encouraging, but I don't think it's anything to cheer about yet because we're right back into the thick of the drought. But it gives you the sense that there is this longer term variability, right? So longer term variability with precipitation is to be expected, and it's related to El Nino and La Nina events in the longer term. We can translate this into a drought index just to kind of draw out. Blue bars are wet periods, red bars are drought periods. And so the ones that really stand out are say like 1956, 2002, and 2011. But that's not the whole story, right? So the local story, as I'm sure you talked about last week, Greg just showed now too, is that it's getting warmer. And so this doesn't have data through the whole summer, and it also mixes in a little bit of coolish temperatures we had last spring. But as we move through this rest of this year and in the next spring, I think we're going to probably set another record locally. But 2017 was the warmest on record in this particular cookie cutout of Cochise County again. But you can see here that this is not decadal variability. This is trend, and it's rising quite rapidly in the last decade, 2 decades or so. So the important thing when we think about drought, and Greg and I have worked on drought for a long time here, and he mentioned this a little bit here, is that when you think about precipitation deficits or being below average or above average, you divorce it from temperature, you're not telling the whole story. So if you add temperature to a drought index, and that's what this particular drought index does, it's called the Standardized Precipitation minus Evapotranspiration Index. So it has both precipitation and temperature together. That increased evapotranspiration leads to stronger drought intensity and more drought impacts. So you can see that the more recent drought period, which looked, go back here, looks fairly even with the 50s, say, for example, the last drought period. We go forward with temperature, and you can now see it's actually worse with the added contribution to temperature. So it doesn't even have to be quite as dry to be even more droughty under these warmer temperatures. Okay, and so if we think about this on the long term, this is the creeping crud of the temperature aspect, even as we are having a highly variable climate, is that even those wet seasons that feel wet aren't necessarily as wet as they would have been in the past with increasing temperatures. So that increasing temperatures increase evapotranspiration, so evaporation and transpiration, pulling the water out of plants. Does it on average over time. So we can still have these really great wet winters that honestly aren't quite as wet as they should be because it's now warmer. And so we also have to keep an eye on, as Greg talked about too, is that the kind of precip matters. The shift from snow versus rain can look like the same amount of total in the rain gauge, but is actually effectively different hydrologically. Okay, so I'll just quickly wrap up here and take some of the projections that Greg was showing for the broader region and just zoom in on it. And so there's a tool that a lot of us use. It's called the Climate Toolbox from the University of Idaho. Some colleagues put together, and you can do it for a location, you can do it for a county, a watershed, a larger region, and so it gives you a sense to play around with. What do the climate models say for a specific location? So I did this for Cochise County. You could do it for Sierra Vista. Okay, and again, I think you probably have already talked about, but these are not forecasts. These are projections, and these are based on these different emission scenarios. And so there are 2 here, and they're very consistent with what Greg talked about as the broader regional trends here. And so we have a higher emission scenario and a lower emission scenario. And so there's a difference here. My window's in the way here. It's as much for the higher emission scenario by end of century, about 8 to 10 degrees on the higher emission, and the change is around 4 to 5 degrees for the lower emission. Again, this is annual average temperature, as Greg noted, but that could be a shift in the geography, from Sierra Vista to Tucson. And as we look at precipitation, there isn't real strong change detected in the climate projections here. And I think a lot of it has to do with struggling to resolve the monsoon effectively, because it's such a nuanced phenomenon for here in the Southwest. And so variability isn't totally locked down. So whether we're going to have stronger events, more frequent or weaker or less frequent isn't real clear here. So there's a bit of a wash here in projected change. But what you may notice here too is that this range of variability actually gets wider. So there's actually more uncertainty in these models out towards the end of century. So we don't really have a good understanding of where precipitation is going to go, but we know it's going to be warmer. So there's a lot of actionable information in just having that. And one of the tools that you can play with on this climate toolbox to really kind of give you a sense here is I did this for Sierra Vista in particular, is it takes the top one is the lower emission scenario, the bottom is the higher emission scenario, but actual summertime temperatures to just give you a sense of what those changes are. So just on average highs, lower emission scenario for the summer of 91 to 96, very consistent with what Greg had said, and the higher emission 91 to almost 10 degrees warmer. So that's certainly something to keep an eye on here. Okay, so to just quickly wrap up, complex variability at weather timescales dominate the hydroclimate of Southeast Arizona, at least high levels of interannual variability. And so it's sometimes hard to notice the changes, especially during those great wet winters or it's a great monsoon season, but the changes are still happening. The climate models project similar, if not higher variability in the future. Precipitation projections have much higher uncertainty, but we know it's going to get warmer. And we know that those warming temperatures are going to increase evapotranspiration. So even if it does, by chance, we have wetter monsoons, we're still fighting this increased evapotranspiration. So you can see the water kind of getting swept out from underneath your feet just because it's getting warmer. So thank you very much. And I'll be sticking around for the rest of the session today, and I'm happy to help field any questions a little bit later.
Thank you very much, Dr. Crimmins. Just getting back to Greg to help get this going. I'll unmute him if he's not already unmuted. Go ahead, Greg, hopefully.
Okay, there we go. Very good. Yeah, so now we will shift over to think about southeastern and southern Arizona forests from Dr. Laura Marshall. And it's a real pleasure to have Laura join us. She recently took part in a series of webinars about the big fires that we had in the Santa Catalina Mountains outside of Tucson this summer, and did a great job.
Great. Yeah, and if you saw that, a couple of the slides are reprised from that. So basically, can we move my video around? Okay, there we go. So I'm going to talk about fire and climate and the forests. And a lot of that is going to be set up on what we did to bring the forests to their current state, which isn't strictly talking about carbon emissions and that sort of thing, but it all comes around and applies. Where's my... Okay, so for Southern Arizona, we have a great introduction to vegetation change and ecosystem type. So as you move up in elevation, it gets cooler, of course, and you go through various different ecosystems. And each of these have their own particular relationship and adaptations to fire. At the very low level, Sonoran Desert, you wouldn't expect fire there at all. Possibly only rarely, there's very little fuel connectivity, nothing to carry fire through until buffalo grass moved in. Higher up, like in Sierra Vista, you get a lot more desert grassland and move into woodland. That did burn fairly frequently in the past. And as you move higher up, you get greater fuel loads and a greater history of fire. So you get very frequent low intensity fire expected in pine forests and higher, basically. And that's how things were like 400 years ago. It's changed a little bit as you move forward in time. And that's because of human manipulation of the forest. Basically, starting in about the 1600s, Europeans started to move thousands and thousands and eventually millions of grazing animals into the western forests. And they graze down all the fine fuels, and that reduces fuel connectivity that helps fire spread. So that starts to cut off fire from these ecosystems that are adapted to it. And then we got really good at fire suppression over the course of the 1900s. Fire was really seen as just a threat to the resources in the forest. It was bad, we didn't want it there. At least that's what we thought. And strategies evolved to fight these fires over time. After World War II, smoke jumpers became more common, and we were able to get even into very remote areas to put out fire. And that didn't affect absolutely every spot of the West. In particular, you can look at the Rincon Mountains compared to the Santa Catalina Mountains here. The Catalinas have a road up them, so it's easy to get up there, easy to put out fire. The Rincons don't. They managed to maintain a lot of their historic, frequent, low-intensity fire regime compared to the Catalinas. And of course, in more recent years, we see that fire is a natural part of the ecosystem and can be a tool for management and restoration, and to promote resilience as we move forward into our climate change future. And the big issue here is that if you exclude fire from a frequent fire forest, you get a massive increase in forest density. And that's an increase in carbon stocks, an increase in fuels on the landscape. And all these trees, in this case, it was a mountain range that I worked on from part of my dissertation. So on the left, we see a great historic photo showing what the caption called good regeneration. But if you leave that alone without fire for 100 years, you get this dog hair thicket that you can't even walk through. And if fire gets into that landscape, it's just going to very easily blow up, burn into the canopies of the large mature trees and kill everything, release a ton of carbon as it does. And it's not just the forests that have been affected by this sort of ecosystem change. This is the Walnut Gulch Experimental Watershed, which is around Tombstone, Arizona. And the arrow here is pointing at the same spot in each of these photos from 1890 to 2006. And through that time, you see a shift from a much grassier ecosystem to an ecosystem full of shrubs. And that's, you can't really track that change like you can the fire change because it's a different sort of tree that you're working with, but it does cause substantial changes to the fuel makeup of the land and how fire will be carried through that landscape. So one more important thing to understand about fire is, well, I don't like to say how good or bad a fire is because it's a fire, it's a natural part of a landscape and an ecosystem, but the effects can be good or bad in human, view, and to some degree in how it affects a landscape. So I think more in severity. So you can get a low severity fire, a moderate, or a high severity that kills off most everything above the ground. And which level of fire, I guess, how severe it is governed by the fire behavior triangle, basically. So climate, weather, and topography. Sorry, I can't see my triangle there. Fuel, topography, weather. There we go. Anyway. And of course, climate change is a part of that in influencing weather. Topography, you can't really change much about, and fuels is something that humans have particularly affected through fire suppression. Oh, keep forgetting to change that. Okay, so how do we know when fires happen on a landscape and that they really were so frequent in the past? We do that through fire scar collection and tree ring cross dating. So when you go out to the woods in these frequent low severity fire systems, trees will sometimes get scarred, but survive the fire, and it will continue to grow until the next fire when it gets scarred again and just continue to grow. So you'll get these interesting lobes if you take a section of like a burned stump. And the fire scar is built into this structure of the tree ring, basically, so you can see almost down to the season when that fire burned across the landscape, at least if it was burning during the dormant season before the summer when the tree started growing, during mid or late summer based on how wide the ring is at that given point, or later in the season. And we can know that exact ring through cross dating by taking samples of living trees, which is usually cores, because you don't want to cut down a tree just to know how old it is. But if you do that, basically these tree species will make one ring per year. Sometimes there's a little bit of variation in what the ring looks like, but it's fairly easy to tell if you have enough samples that this, one ring here is, 1997. And if you count back through time, you can match up the patterns which form as a result of climate. In more arid landscapes like Southern Arizona, the ring width will be very dependent on how much rain you get, mostly during the winter season and then summer, because that water is all stored in the landscape. So basically, when you get a very dry year, you get a very skinny ring. And those very skinny rings will be the same across entire mountain ranges. So if you go back and find this dead stump and cut it open, you can match a certain pattern of skinny rings to living trees and know that that fire was 1748 for sure. And this is kind of a big graph, apologies, but basically every horizontal line here is a site with a few trees, and every vertical line is a fire scar that was taken at that site. And so where the fire line up vertically, that's where fire was burning across the landscape in the same year. It could have been different fires. It could have been one major fire like the Bighorn Fire that we saw. And when you see these, very long link ups where everything was burning, you can be pretty sure that that's a climate driven fire. When it's drier and more arid, especially following a wetter period, is when you get these big landscape scale fires that burn across. And okay, this chronology in particular is from the Santa Catalina Mountains. And you can see that from the late 1500s through to 1900s, fire was burning very frequently across this mountain range, almost every year in some locations, and in large, events, maybe every 10 to 20 years. But after 1900, it basically stopped. And that's when fire exclusion really kicked in this mountain range. So people were putting out the fires. There was a fairly wet period at the beginning of the century that also helped people to put out fires, but mostly that's our actions. If you look at a similar figure from the Rincons, you'll see fire continuing through the 1900s, at least at a small level. Okay, so now to get more specifically into climate change. Yes. We see with climate change, fuels will dry out, so you get higher fuel aridity. That means as you move forward in time, it's increasingly dry, the fuels dry out faster, and you get larger forest fires. So on this axis, it's fire area and how dry the fuel is. And you can see the last 15 years, well, up to 2015, all fall on the very dry, very large fire side of the graph. We're also seeing a longer fire season. These are a little bit harder to interpret. They're kind of closer to this average mean line, but you see that definitely in the later years, you're getting a lot more days with high fire danger. So that's the very dry, hot, and often windy days that push, extreme fire behavior. And I know in the Bighorn Fire, the one day it blew up and ran up the mountain towards Summerhaven and burned 12,000 acres. That was a really high fire danger day, a red flag warning. Okay. Lost my clicker. Okay, and also with climate change, we're projecting a big increase in annual area burned. We've seen a little bit of that in the last few years, but this is using modeling to look forward to 2010 to 2040 and to compare it to the 1960s to 2004. And so basically red is a huge increase in the area burned in a year that you predict from climate change. So this is almost over 1,000% more than burned in the 1960s through 2000s. Though remember, a lot of that period was during fire suppression. So you got much smaller fires, fewer fires than you, well, not necessarily fewer, but definitely smaller than you would have under more natural conditions. And also, I have to point out that it's not necessarily a bad fire. If you have a larger area burned, you could be burning low intensity, promoting more of a natural fire regime across some of these areas, or you could be having a high severity fire that burns everything, and that's that figure on the left. So even if area burn goes up, there's a chance you might be able to have that low intensity fire regime. Now, and I'm going to turn it around and look at how fires influence climate change, because of course, when you burn, you're releasing a lot of carbon and a lot of smoke into the atmosphere, because trees are basically big sticks of carbon on the landscape. And the larger, older trees are where most of the carbon is. All those little tiny stick trees that have grown up in the last century, there's not actually that much carbon in them. So if you take those out of the equation and keep the large trees on the landscape, you can actually keep more of your carbon in the forest and on the land. So in this figure basically shows carbon emissions from fire from 1997 to 2019. This year might be a little higher. And also in the lower, just looking at the fire emissions, it splits it up by region. So this is a bit broader than just southern Arizona, but really what you can take from this is it's the tropical areas burning that have the biggest carbon influence on the emissions in terms of fire. And even in a bad fire year, the total emissions from fire is relatively small compared to overall fossil fuel emissions. So there's one more factor with more graphs. I can't resist a good graph. But basically, after fire, climate will influence what can come back into a system. So with climate change, with hotter and drier weather and drier soils, seedlings are going to have a much harder time to establish. And that's assuming you have surviving large trees to provide a seed source for these seedlings. So conifer seedlings in general have a much stricter requirements for what they can survive than mature trees. So you need it suitably cool and moist. And in these figures on the right are showing that there's a pretty strict threshold for how hot and dry it can be and how dry the soil is for whether or not you'll have seedlings grow. And as you move forward in time, as in this lower graph, the periods of times that meet those conditions are decreasing substantially in the Southwest. And this is a fun paper that came out last year. And there are some seedlings that are growing where you have good microsites and microclimatic conditions. So small areas that are more protected, they might have slightly moister soils. Seedlings can still establish in those locations, as seen in this photo, which was a bunch of seedlings that established probably around 2010. So it might have been one of these little dot events on the right in an area that had been thinned previously. So there was like a thick layer of mulch on the soil, trapping all the soil moisture in. So even though it was dry, that particular area was able to support seedlings. But in general, it's going to be hard. And in the lack of easy recruitment of forests, what's going to happen? You might see forest area shift from conifers to more oak-dominated systems. Oak will just resprout after fire. It doesn't need to reseed like conifers do. So it has a much faster time to get going and can block out, competition through competitive, competitive interactions can block out those conifers coming back in. When you totally lack seed trees, no seed source around, say from a very severe fire that burned through an area and killed all the large trees, you might have a switch over to grass, as this area in a Colorado forest that I visited that had something like 20,000 acres without trees that a fire had burned and killed off all those trees. So that area is going to have a very hard time becoming forest at any time in the next multiple centuries, probably without substantial human influence through planting. Now, if you are able to, keep fire at a, more mixed to lower severity, get it back on the landscape in a cooler, season where it's not going to have that extreme, climate-driven explosive behavior, you might be able to instead promote resilience in the forest and remove some of those smaller, denser patches while retaining those large mature trees. And that's kind of the more hopeful, view of what we might see in the future. And I'm trying to keep track of time, and let me know if I'm talking too much, but now we're going to get into just a little bit on what you can actually do about this. If you remember back the fire behavior triangle with fuels, weather, and topography, the big one that you can deal with on a personal or even a management level is fuels. And that's controlling what's around your house and what's in your community, basically. There's a lot of information out there if you Google FireWise on how far, it's good to have, the heavy fuels pushed back from your house or from your area. And that varies depending on what ecosystem you're looking at and how, what kind of fire is likely. If you're expecting a, extreme event blown through the crowns of the trees, that's going to be a lot harder to, adjust to deal with. But if you have a grass fire coming at you, by taking reasonable steps to move back, keep that fuels, back from your house, you can much more easily protect your own personal property and your community. And looking at the more wild areas around their communities, there's this multiple projects going on to look and work at a landscape level with fire. And this one in southern Arizona, it's called Firescape. And it's bringing together basically many stakeholders, many land management agencies and communities to build large treatment areas to reduce the risk of these extreme fire events. Though we did just have the bighorn that was fairly extreme. So hopefully they'll continue to work on that. But basically they build a large network of area and stakeholders to build large treatment plans that you can apply across basically as very broad areas, because this legacy of fire suppression and climate change affects basically everything forested in southern Arizona. So you have to build at a large level to address these issues. And this is just a map of the Huachuca project, which is something like 400,000 acres around Sierra Vista. And if you look at the actual treatment plans that they've put in place, you have a mix of prescribed burning in the more remote mountains, thinning and burning in some of the high elevations of the Huachuca Mountains, and then thinning at lower elevations. And that's all an effort to reduce these, built up fuels by thinning out just the smaller trees. Generally, they have very strict requirements on what you thin. It's not just go cut down everything, but it's all to promote the eventual return of reasonably frequent good ecosystem promotion of fire in this area. And I think that's the last slide I have. Okay.
Thanks, Laura.
Stop that share. So sorry, that was a lot, and I just get really excited talking about some of that. So if you have questions, please let me know at the end.
So thank you. And so now we'll just transition to Holly's presentation. And let me see, I'm going to need to share my screen to show Holly's presentation. Holly, do you want to start with the slides or with the video?
She talked about having some audio issues and was talking about calling in. I am trying to see though, but then she said that she was okay. So I'm trying to determine, she doesn't show a microphone on her Zoom identity. So I'm trying to figure that out. So here we go.
Yeah.
Okay, I'm trying to unmute. Yeah, I don't see you. Hang on a sec. Let's see. Sorry about this. You should. I'm going to unmute. Okay, let's try that. Okay, Holly, can you try talking now?
Okay, I think I'm running.
All right, cool.
Great, thanks, guys. Yeah, my phone was on a separate screen than my video, and I apologize for that confusion. But it's a pleasure to be here tonight. Thanks so much. I think we'll start with the video. I know we're going to kind of be tight on time tonight, but it's really easy to take things for granted that are in your own backyard, and the San Pedro is in our backyard, and it's a very special river. And I wanted to start with this video just to share with you why I think it's so special, and many others do too.
I think this will do it. Let's see.
Yep. Not getting sound.
No sound.
Yeah. Did you enable the sharing of sound, Greg or Holly, on that?
I don't know how to do that.
Under the share screen, you pull it up on the bottom left corner, there's a little check that says to enable sound. I can't do anything with it because it's on your end.
So,
Sorry.
so you were saying, you were trying to give me direction on this. So you're saying under the microphone symbol, is that where I have to look?
Let's see.
So it's,
When you start to the share screen, when you're about to pull it up onto the screen, everybody can see. On the bottom left, there is a little icon that says enable sound or something like that. So
enable sound.
I see Holly, so that's good.
So I don't see enable sound.
Yeah, I can't help you because you have the on your end, I'm afraid. Let's see. It says share computer sound or something like that. Heidi's trying to help us out. When you click on the share screen,
Share screen.
so back out.
Yeah. Okay, I'm stop sharing.
All right, now go to share screen.
Okay, I see. Now I click share computer sound. Okay.
Yeah, there you go.
Sorry about that, folks. Let's try that again.
That should do it. There we go. Good.
Thank you.
The San Pedro is simply a magical oasis. I grew up back east. I know a lot of people that come out here from more humid climates will look at the San Pedro and say, that's barely a creek. And actually, it's more than a river. It's an entire ecosystem with this riparian forest and these lush trees and wetlands and different habitats around the river itself that sustain an amazing diversity of wildlife. Species that come just as far south down from the Rocky Mountain region, species that come just as far north up from the Sierra Madre in Mexico. And then in the east and west sides, we get species from both the Sonoran Desert on one side and the Chihuahuan on the other. And all these different wildlife kind of collide on the San Pedro and create this amazing spot of richness.
Just so cool. There's nowhere else I know of where you can just walk 10 steps and you go from one environment, one habitat to a completely different one. If you were ever to come down here at the crack of dawn and go into those, or even a little before, and go hang out under that canopy, it sounds like a jungle in there. There's so much bird noise, the animals come into life. It's just really cool.
This part of Arizona is actually at a biological crossroad. In this 750-mile stretch of what is largely desert or semi-arid grassland, you've got just this one river. It's a unique ecosystem and one that's worthy of protecting.
It really is a river of life. It's a phenomenal place teeming with life.
Thanks, everyone, for figuring out that technology. I appreciate it. And I wanted to jump into just a couple of slides. I know, again, we have a short time tonight, but I did want to talk about the river and how we can be good stewards of the river going forward. It's a challenging time, to be honest, with all the variability in climate and the extended drought. The lifeblood of rivers is water. And water has always been scarce in this area. It's becoming increasingly scarce for multiple reasons. Obviously, the climate is part of it. So is our water use. And so how can we be responsible stewards of the water resources that are available for both people and nature? And it is a really complex thing, and I'm going to go through it really quickly, but I do want to encourage you all to think about it and to be aware of our roles in making sure there's enough water for the future. So let's try to just move forward here pretty quickly. And my slides are going to be, I'll probably see them way later than you, so if I have a delay in saying anything, that's why. Sorry. But this is a map of our watershed, and it shows our river flowing out of Mexico into the U.S. And near Palominas, it flows north, as you know, past Sierra Vista, past Fort Huachuca, and it keeps flowing north. This is actually only the upper half of the San Pedro River. It doesn't show the lower half where it actually flows into the Gila River eventually. But that pink, long, narrow area along the river that's shown is actually the BLM's National Riparian Conservation Area, where so many of these wonderful habitats and wildlife still persist today, and is a real focus of our conservation efforts. But let's talk about how this river continues to flow, especially during long periods without rain. And obviously, this watershed itself is defined by mountain ranges. And those mountain ranges, as has been mentioned, they're higher elevation with more precipitation than we get in the valley bottom. And so because it rains more in the mountains, a lot of the water that comes down into the valley flows from the mountains down to the valley floor, and then it sinks underground into our groundwater and our aquifer, which is invisible to us and very hard to remember that it's even there, frankly, under our feet every day. But what is an aquifer? Well, it's soil and rock full of water, but that water is slowly moving towards the lowest part of the valley, which in our case is the San Pedro River. And that groundwater is an essential component of keeping that river flowing during long periods when there's no rain. So when we get big floods, obviously we get these big flood flows and we get a lot of surface runoff. And the San Pedro is actually one of the few rivers that's not dammed, one of the large rivers that remains undammed. And that actually keeps it very healthy for all kinds of other reasons that I won't talk about right now, the fact that it's free flowing. But it still depends on this groundwater resource. For especially those driest, hottest times of the year when the wildlife is just drawn like a magnet to the river for its water and its shade and cooler temperatures. So if we weren't using groundwater, it would have shown, those continuous arrows. But when we insert wells into the picture and use some of this for our own consumption, obviously that intercepts the groundwater as it's flowing to the river. And every gallon of water that we pump for any reason is one less gallon that could have eventually made it to the river and supported the wildlife and the ecosystem of the river. So we have to be really careful and very conscious about how much water we take out and where. And obviously the most important thing we can do is to conserve water and to make sure that we're not wasting water and that we're being really efficient. And thank goodness there's a lot of ways that today we can be more efficient with water. Even, the fixtures that are sold in Home Depot are much more water efficient than they had been in previous decades. But it's still a real consideration for us because when we pump, we actually draw down that water table and the groundwater starts to be depleted around the well. And that's when you might have heard this term, a cone of depression forms around pumping centers. And that means that the groundwater the level of that water table starts to drop. And if it was pumping particularly near the river itself, it could reverse the direction of those groundwater flow paths and actually even remove water from the river. But even if it doesn't pull it out of the river, what it does do is intercept that water coming towards the river. And this is a really major concern for us. And there's a lot that's been done for decades here. And I think in many ways we've provided some really good examples of both the science and the projects that can be done in terms of water management, but we're still not finished. Let's just move to the next slide and we'll kind of talk about the big picture. Again, these are kind of projections, simulated models that can tell us kind of given the information that we do have, what can we expect in the future? And this shows red areas where those cones of depression or the groundwater is expected to be pulled down from being pumped out of the aquifer. over time. And on the left, it's that's in 2000, and then it shows 2050 and 2100. And it shows basically 3 pumping centers, one around Sierra Vista, which is our municipal water use. There's another one around Palominas, you can see, and that actually had more agricultural water use in the past than it does now. And that cone of depression doesn't grow like the municipal one over time because of that change in land use. And then you can also see down in Cananea, the industrial water uses with the Cananea mine and the impacts that would have. So this is kind of, if we do nothing, what we can expect to have happen. And of course, we don't want to do nothing. And let's talk about what we have started doing. Okay, computer, catch up with the rest of the world anytime now.
We see it.
Do you see it? What do you see?
We're seeing Sierra Vista effluent recharge.
Okay, yeah. So one of our first larger projects in the area to replenish groundwater supplies was the City of Sierra Vista's effluent recharge facility. And actually, you can see on the left there, this is when they were just renovating that facility. This is back around 2002. They used to take all of the wastewater in Sierra Vista and treat it, and then use it actually for the irrigation of alfalfa fields. You can see the old crop circles there where they just, wanted to just get rid of it by using it for irrigation. And a lot of that was evaporated at the time. And then around 2002, there was the recharge ponds constructed in the upper right-hand corner, which were designed to actually put that water back into the ground and to kind of recycle on a grand scale, if you will, the water that had been pumped. And that project has been very successful. It has increased groundwater levels for miles around the facility. And it really kind of became a pilot project and an example for additional recharge projects that we'd like to make sure are built along the river to further protect it from some of the effects of both climate change and pumping. The thing that's great about treated effluent is it's a very reliable source of water. It receives the same amount, of water into the facility pretty much all the time. Obviously, it depends on population, but it doesn't vary a lot like stormwater would, which is more dependent on precipitation. So over time, there was a lot of science done by the Upper San Pedro Partnership. That was a large consortium of interest in our area, 21 different member agencies. But about 5 of those agencies decided to actually start building some projects along the river that could best sustain it. And there's a website address there if you want to learn more about these projects in the bottom of the slide. But it involves the City of Sierra Vista and Bisbee, Cochise County, the Hereford Natural Resource Conservation District, and the Nature Conservancy. And so what we did was we used the computer models, like the one I showed you before that showed us what would happen if we did nothing. And we said, well, what would be the best things to do? Where would be the best places to recharge? And how can we ensure that we protect the river through additional recharge projects? And obviously, there's a lot of assumptions in these models. And I have spoken with Greg multiple times, and I intend to talk to him a lot more about how to make sure to incorporate the climate change aspects into these models, because there's still a lot of uncertainty in them about that. And we have a lot more work to do to really understand how to be successful at this given climate change. So a big caveat there that we don't have all the answers in terms of will this really be able to keep the river going regardless of these different climate scenarios. But what we have found is that there are key areas to put the water back into the ground, and that's what's shown here in green. Multiple projects. 3 of these project areas were actually subdivisions that went bankrupt back when the market crashed, and the Conservancy was able to purchase these properties through funding from Fort Huachuca and turn them into these recharge and water protection projects, which was really fortuitous and to me really shows the power of collaboration and what can be done when we work together. So some of these projects are already built, others are not. We do not have all the funding to do these projects. Some of them are very expensive projects. but they will be essential for us to complete in the future. And I think it just really is important for the community to be aware of the values of the river, and to support those who are developing the science and the projects to protect it over the long term. And there's so much more I could say, but it's 7:56 and I will stop. So, yeah.
Thanks, Holly. Let's see. So at this point, we have very little time unless people are willing to hang in there for a little bit longer. Maybe we could just take a couple of questions to get things started.
Yeah, we can extend the time for us. We're fine. So, you know, people can stay and have questions, want to have them addressed, at least some of them. And we can also see about next week. You could put them in the chat as well, and we can try to address them this next week if we can't this. Or we can find other ways to address them too. So go ahead, Greg, if you would like to host the question and answer.
Sure. I guess we could just have folks unmute themselves if they want to ask a question, or you could raise your hand or submit it in the chat window.
Anybody have any questions that you'd like to lift up?
Maybe you're all fatigued by the barrage of information.
It was a lot, but it was fascinating and important. Oh, there's one, Dottie.
Well, I have a question for Laura. There were some great charts that you had put up, and I'm wondering if any of them, especially the ones around the Huachuca area and Sierra Vista area, if they are available to the public.
Yes, pretty much everything I was using is either from a published publication or occasionally a news article. I can send my material to Greg and he can send it out with references if you want to look.
Oh, great.
more.
That would be wonderful. Thank you.
Was there something in particular that caught your eye?
Well, the part about the oak and the conifers, but then she had some good slides on the fire escape preserve in the mountains.
Mm-hmm.
And the Huachuca Fire Escape Project. I'd like to see those because I like to share them with some other people. And also, Holly had some good ones too.
Yes, I can get them.
Thanks.
Thank you very much.
Yeah, we'll get those to you. Anyone else have a question, comment, a wish list for things for us to follow up on?
Doug.
Yeah, I'm looking at thinking about soil sustainability, and Laura was talking about the seedling regeneration. A couple of decades ago, I attended a science camp in Prescott, and they were the expert was talking about the Amazon rainforests and the burning to make farmland, but that soil gets depleted quite quickly, and they have to do some more burning to get some more soil. But the native plants, the native trees, especially the diversity, cannot come back because the soil is destroyed by the planting and by the lack of canopy. and the nutrients being sucked out of it. Is that the case that we're looking at here, that we cannot regenerate the same plant life? Laura?
Let's see. So it depends on how badly the fire affects the soil. In the Amazon, it's really a particular case. They have really different soils than you find here. Fire, if it's very hot, very severe, can basically destroy the chemical makeup and bounds of the soil. And that can be a lot harder for some species to come back in. There are a lot of species that are adapted to specifically come in right after fire. And those do well in most cases. And of course, with restoration projects and treatment right after the fire, we take steps to try and preserve the soils and keep them on the landscape. So that by sometimes spreading straw, sometimes direct seeding, to basically try to encourage something to grow back the next year. It's not really an issue in anything but really the most severely burned areas, I believe. And if anyone else, Greg or anyone else wants to jump in on soils, please do. Most of my experience is above the ground layer.
In the Amazon, that forest is not fire adapted the way our forest is that right?
Not in the wet Amazon. And that they really are having very serious issues with burning into the wet Amazon right now. There are other areas that are drier, have a more pronounced dry season, that do have some level of natural fire and fire regime that's on a more frequent basis. But that's probably outside what you'd think of the traditional Amazon itself.
Thanks.
I have something. I don't know if it's time to discuss it. I was thinking Holly had brought up the San Pedro National Riparian, I think they call it SPRINCA for short, it's in an acronym, but it's managed by the Bureau of Land Management, as I understand. And there are contracts or compacts or whatever they call them from many years ago having to do with land use for grazing and for all kinds of things. And they're trying to preserve the water resource for the riparian area and to maintain it. But that's sometimes at conflict with, there are then people who want to use the water, again, using it for domestic use, and for agricultural use, drawing water through wells. And that, of course, takes away from the natural resource of water that goes into the natural riparian area. And so there's this conflict. And I'm sure can't answer the whole thing right now, but perhaps if you would consider next week, if you're going to be back, and I hope you are, then maybe come back with some insight on how that conflict might affect the water resource.
Jimmy, you raised some very valid and interesting concerns that I certainly can't address in a short period of time, but I'd be glad to come back anytime and talk to you and everyone about them.
Okay. Thank you.
Thank you very much.
Bases.
All right. Any others before we depart? Obviously, there's a lot here, and we appreciate the information. Again, you can review this all on our website, as also on Facebook, and YouTube. So those are some access points. if you want to review what has been said tonight and look at things in terms of the slides especially. Yes, Gail.
I'm wondering, I guess, Dr. Garfin would be directed to you about the lower amounts we're putting into the air as a result of not driving so much. I think there's been a tremendous impact we've noticed as a result of COVID, pollution, etc. Do you have a sense of how we can affect that ourselves here in the state? And do you have any statistics on that? Are you looking at the pollution reduction?
I haven't been tracking the COVID-related decrease in emissions, but I have noticed a few news articles about that. Certainly it was very striking back in March and April when it seemed like there was a sort of a global shutdown of business as usual. I think we'll be able to talk next week a little bit about how we, some of the best paths for reducing emissions in Arizona, and also I believe we're going to talk a little bit more also about electric power generation and ways that we can maybe use different mixes of fuel types to reduce emissions.
California today, I read, is banned. In 15 years from now, there will be no more gasoline-powered cars sold in California.
Wow. Yeah, well, this is probably a good segue then into next week. But before we do, again, thank you so much to Mike, Laura, Ollie, Greg, and Laura. Thank you so much for your information, for all that you're doing, for trying to fit all this in this time period. I think you did a good job in working with us on that, and for your graciousness and generosity and sharing your time with us all. And next week, we will be looking at, again, as Greg said, renewable energy efforts and other hopeful steps in mitigating the effects of climate change. Like Greg said, this is a lot of doom and gloom. And that's a little, kind of tongue-in-cheek type of thing. And yet also it's a reality. And that's part of what we're trying to do is learn about the reality, face the reality, accept the reality, and then what do we do about the reality? And that's what we're hoping to look at next week more, that there are things that we can do. And also tonight, we heard of some of those things. And thank you for bringing up some of the things that are being done, whether it's with the San Pedro or other things in Southeast Arizona. So we're also going to hear from Nicole Hill next week from the Nature Conservancy as well. So look forward, that'll be again at 7 o'clock start time next Wednesday, the 30th. And if you have not registered for that, it's a separate registration. Please look on our website for that, or I can send it to you if you like. But that information should be pretty available for you.
So is that a change? I thought it was 6 o'clock.
No, it's been 7, right, Greg? We've talked about that. Yeah.
It is 7. Okay.
Yeah.
Okay.
We're trying to work with these good folks from the U of A and so forth in their schedules, and we appreciate very much that that's happened. Any other closing questions before we sign off tonight?
Some sort of message.
Unmute that. You can facilitate.
Mute.
Yeah, you're unmuted now. Great, Glenn, you have been, sorry. Go ahead, Glenn. Apologies.
He's muted.
Okay, it wasn't working. I've been trying all night.
I apologize.
3 questions. You cut me off when I've asked too many. For Holly, a lot of recharge basins have been developed beyond the ones you were talking about. Like I can remember one at the mall. That's the only one I've ever seen fill up. It's a small one. And understandably, I think it's taken parking lot water or other water, but there's a whole bunch at the fort that I never see fill up. They've done quite a bit. So a lot of money's gone into this, but if it doesn't rain, as we are finding out, it's being wasted, right? The capability's there, but the reality of the whole thing is failing.
Holly, did you want to respond to that?
Yeah, just real quickly. So a lot of those basins were constructed primarily for flood control, not for recharge, but they have some recharge benefit. Those smaller basins like around the mall, they really are for handling stormwater in the urban area, not so much really just intended to increase the water to the aquifer. And we could talk more about that some other time too, but it's really the recharge projects that are right along the river that can help it the most. Yep.
All right, thank you. And then if I can keep going on short answers, Mike Crimmins, you talked about on one slide emissions and the potential. You had a graph and it had blue and red dots. I don't have the number of the graph, but you talked about emissions and the potential you have to predict or model from that. And I wasn't sure how that would be done with the available information on that graph.
That's right. So there are two concentration pathways, radiative concentration pathways that are based on IPCC, Intergovernmental Panel for Climate Change, models that are through working groups where they do socio-political, geopolitical, technological, kind of future technology estimations on what those greenhouse gas emissions will be out through end of century. And so I only showed you two, but there are many different ones and they all have different traces and different lengths of time that will track the different emission scenarios. So there's scenarios.
I'll say the one for Cochise County that you did for us had emissions being improved, I guess it was. And I took that to mean combustible emissions. Is that what, or is that forest fire emissions or what type of emissions?
Yeah, it's not local emissions. It's still global emissions run through a global climate model. But then we zoomed in on Cochise County to look at the climate changes from a global change emissions.
Okay, thank you.
Yep.
And then I'll toss this one out. Greg, you seem like the best one to take it, or Mike. The research articles I've read about modeling climate say that we're really poor on considering the stratosphere, and particularly the SOX considerations, the inputs there. Now, this goes back a few years at least. Do you agree with that or know about that or have a comment about that is my question.
So are you
underrepresented, in other words?
So with the SOX, you're talking, particularly about particulate that might cool the atmosphere?
Yeah, exactly.
Mm-hmm.
I'm hitting you with a fastball. So if you don't want to say anything, that's fine. It was just a curiosity on my end. So.
Yeah. So the thing I could present some information on this next week, but by and large the models have done a really good job with global temperature. And they tend to be more faithful at larger spatial scales. So as we go from large regions to continental and global scales, they tend to be, I guess what we might call them more accurate at those scales than if we try to zoom in to a particular place. I'm not aware of modeling issues related to the stratosphere. Do you know more about that, Mike?
You have to unmute. There you go.
Yep, sorry. Yeah, I think, Greg, I'm thinking back to one of the figures from the IPCC that had the the uncertainty around the radiative contribution for different things. And so,
okay.
yeah, and so stratospheric
Yeah.
aerosols, there is uncertainty around them, but the uncertainty of their contribution is relatively small to the overall contribution of greenhouse gases. So even if we tightened that uncertainty down, it wouldn't account for anything more. It would account for more. It certainly would help improve, but it wouldn't wash out the contribution from the greenhouse gases.
Yeah, okay. I know exactly what you're talking about there. Yeah, so I could bring that
Close out
to
with one more for any of you. There was a paper written many years ago that's famous in ecology called by Garrett Hardin, I think was his name, Tragedy of the Commons. And basically what I got several things out of it, was that if everybody's not playing the game, and I'm now shifting over to the Kyoto protocols and the protocols that have come after, people have signed on, there's no enforcement, there's no penalties for not meeting it, the big players aren't playing. So you take somebody that does, a country that does everything right, they're just a small place on the earth, and if everybody else is polluting or contributing in a negative sense, what have you won? That's what I'm looking at in the big picture. And that's a hard one to answer, I'm sure, but
yes.
any
So
comments?
yes.
Yeah.
So you're getting into, global climate policy and the degree to it. It's a little late to try to get into this in any depth, but you might recall there was a meeting of the various countries back, it was either 2015 or 2016 in Paris, where countries came to voluntary agreements for reducing emissions. And so what can I say about that, other than to try to bring some information next time? I don't even know, frankly.
It's too big a bite.
Well, it's not. I tend to focus on the Southwest region,
Okay.
but I can find out from one of my colleagues where to go for information on what sort of monitoring has been done about tracking
compliance.
The voluntary compliance with that. I mean, your overall point is on the money. If people aren't living up to their commitments, then it's hard for us to effectively reduce emissions and get at that root cause of climate change. And given that sort of challenge, one of the things that we need to do in addition to reducing the emissions is to have plans to adapt to changes that are projected in the climate models. And those are some of the measures that Holly and Laura talked about in terms of reducing the risk of fires and trying to have a fire management policy that allows for more frequent but lower intensity fires, and also to do everything we can to bolster the flows in the San Pedro River and other water supplies.
All right. I think we're gonna. Yeah, thank you, Glenn. I please don't take it personally. Just chalk it up to not as expertise with the Zoom stuff, but I think we'll pause there till next week, if that sounds okay. And if you have continued questions and comments, you're welcome to send them to me, or like I said, put them on the chat or to our website. And again, my email is simply pastor, PASTOR, and the initials of the church and our state, S Sam, E Edward, L Larry, C Charlie, A Apple, Z Zebra.org. And I'd be happy to pass them on or make sure we can address them when we can. But so thank you so much for all your time and your focus and staying with us. And we hope to see you all next week, either on Zoom or on the live stream. Any last comments, Greg, you want to make before we end this?
Just thanks to my colleagues here for your effort and your presentations and for hanging in here for an extra half hour, and for everyone else for tuning in and asking great questions. Thank you. And thank you, Pastor Moore.
You're welcome. Thank you so much. All right. Blessings to all.
Be well.